Welcome to Embedded. I am Alicia White. My co-host is Christopher White. This week we're going to talk about satellites, specifically CubeSats. And we have Jordi Puig-Suari, professor of Aerospace Engineering at CalPoly, and he's one of the organizers of the upcoming CubeSat conference.
Hi, Jordi. Nice to talk to you today.
Hi, guys.
So that was a little bit of introduction, but could you tell us about yourself as though you were on a panel at an engineering conference?
Okay, just a little bit about myself. I'm Jordi Puig-Suari. I'm a professor of aerospace engineering. I'm an academic. Started my career dreaming about airplanes and satellites and things like that, and went to school and ended up teaching aerospace, which is a wonderful thing to do. And I was lucky enough that because of my interest in teaching and the fact that at CalPoly, where I was teaching, we pride ourselves in learn by doing. We want our students to do what they're learning. Since we were teaching spacecraft, we needed to figure out a way of getting them to actually build spacecraft and fly them. And at that time, the student satellite market was very small, and it was very difficult to get those satellites built and flown. So we got together with Stanford, with Professor Bud Twiggs there, and came up with this idea of doing much smaller spacecraft and kind of standardized spacecraft for students, which was the CubeSats. And it's one of those, the rest is history type of events where we managed to kind of have a significant impact on the industry, quite by surprise to everybody. And that has kind of occupied a large percentage of my waking hours for the last almost 20 years, both in academia and now more recently in the commercial side, where we started a small company that's not so small anymore called Tyvak, based on the same idea of building small satellites at a lower cost.
Excellent. And we have questions for all of that. But before we dig more into CubeSats, I want to do lightning round, where we ask you short questions and hope for short answers.
Okay. You may get long pauses, though, but go for it.
I could take those out. I'll go first?
Yeah.
Favorite airplane or otherwise identified flying object?
Oh, gosh, that's an easy one. My favorite airplane is the Mosquito, which is for airplane buffs, is a well-known World War II British plane. But it was a wooden airplane that was, at the time it came out, it was one of the fastest airplanes around, and it could do anything. And it was extremely capable, and I've always liked it. I don't know why.
Kerbal Space Program. Is this the ultimate evil or something every first grader should have the opportunity to play with?
Which space program?
Oh, Kerbal Space Program. It's a computer game that actually uses orbital mechanics to launch rockets.
Oh, yeah. I think I know which one you're talking about. I think space simulations are wonderful, and anything that gets students to understand travel in space is not like Star Wars, where you point and shoot and go in a straight line. It's a great thing.
Favorite man-made space object? I'm sensing a theme here.
Ooh, favorite space. CP4, which was our first CubeSat to operate in space.
Okay.
Because my team built it, so I'm biased.
That's fair. Okay, what about the whole solar system and things that are still up there? Favorite solar system object?
Favorite solar system object? Wow. Voyager.
Yeah. That's pretty good.
It has to be Voyager, because it's going places.
A few thousand more years and we can't even call it in the solar system anymore.
Right. Exactly.
Well, they already sort of said it depends on your definition.
I know.
Yeah.
Favorite movie or book that you encountered for the first time in 2016?
Oh, the new Star Wars movie, Rogue One. That was good. As a little kid that remembers sitting on the original Star Wars, watching the movie and going gaga, that prequel was very special.
Yes. Okay, this one's a little strange, and I'm hoping you know about this animal. Have you ever touched a pangolin?
No, and I've heard the name, but at this moment I don't recollect what they look like.
They're the ones that are super armored on the outside, and they curl
like-
up into little balls.
They're like
With the
anteaters with
prehensile
armor.
tail. Yeah.
Yeah.
Okay. Well, I think that's fine.
Nobody touched any penguins. Nobody's touched any pangolins.
No.
Gotta
Touch a
keep
chick,
asking.
but that's as exotic as I got.
Okay, so now that the important stuff's out of the way, CubeSats. I have one thing that is sort of a problem with CubeSats, and they're not cubes. Is that right?
Well, you are correct. But they were cubes when we started. You need to understand how little we knew about how to standardize things. They are cubes. The thing that was very interesting is we started with a 10 centimeter cube. And then later, after we make that decision, we decided we need a way of deploying them into space. And for a variety of crazy reasons, we decided to put them in a deployer with 3 CubeSats inside. And then we realized if we put the cubes next to each other, they're going to bunk into one another, and that's not a good thing. So we added these little, 6 millimeter feet on the corners, and that took us out of spec. But that's the story behind that. The main spacecraft dimension is still 10 centimeters. And as you start going into 3Us, which is basically adding up the 3 CubeSats in a deployer and making it into a single spacecraft, then those 6 millimeters keep adding up, and you end up with very weird dimensions. But that was never our intent. But I think it's close enough for engineering.
10%. It's fine.
Yeah.
You are co-inventor of this standard.
Yeah.
And you started out wanting, as you mentioned in the beginning, wanting to do this for students. But it has become an important industry standard. When we've talked to the Planet folks making flocks of imaging satellites, and they were all over how many U's their satellites were.
Yeah.
How did that transition happen?
That's a very interesting question. That's the $1 million question, because if the better we understand that, the better we can maybe try to do it again, and make revolutionary changes, not just in space, but in all kinds of areas of engineering and science and technology. There's a number of things that happen. The first one that's actually very interesting is that the requirements for these vehicles were zero. They didn't have to do anything because their primary objective was to teach students. And in some ways, they didn't even have to work when they got to space, because most of the learning the students get is before they fly. Is the design, the integration, the testing in particular was something that we were really having a struggling time, or we were struggling at the time trying to get the students to get experience in flight testing and doing vibrations and thermal back and all the things you need to do to put a spacecraft in orbit. So all the satellites needed to do is train students. And that allowed us to take a tremendous amount of risk. And it also meant we didn't really need a lot of funding. So that's the first, important piece of information about the program, is that it wasn't on anybody's, technology roadmap. Nobody really needed it. It just happened. The thing that followed that was very surprising to everybody is we had a bunch of really bright students, and it's basically racing. We put them in a highly constrained environment. They didn't have enough resources to do what we wanted them to do, or to do anything interesting. We expected them to build a bunch of Sputniks, and that would have been wonderful. But they were not happy with that. They wanted to put cameras and sensors and experiments and all kinds of stuff. And what they did is they said, okay, we cannot build these things the way traditional space is building spacecraft, because then we cannot do what we want to do. So we'll start doing it our way and see what's necessary. And interesting things happened. They started to take a lot more risk and eliminate a lot of the redundancies. That was one of the first things that happened. We will have one battery and we'll have one radio, and we're going to take the risk that things may go wrong. And then they started looking for the highest performance components they could find. And those were not anywhere near the space parts that we used on big spacecraft. They were all commercial off-the-shelf components on cell phones, on laptop computers, all things like that. And they started launching these things, and they worked. And that's something that was, at the time, impossible for the main space industry to do because they couldn't take the risk. They were always using well-understood, highly reliable, flown before parts, which meant they were really falling behind the computer revolution because they couldn't keep up. If you needed something to fly for 5 or 6 years before you could use it again, or you could use it for real, that meant you started 5 years behind the curve as far as the latest technology. So that was very interesting. And when they started working fairly well, industry started to pay attention because the value proposition changed radically. You had lower cost components that had higher performance, but higher risk. And a few people in the commercial side realized that, well, you can make it up with numbers. I can launch 10 satellites, probably in some cases 50 satellites for the price of one of the traditional spacecraft. And that allows me to take some risk. And I can use the latest technology, and that allows me to get the performance that a much larger spacecraft would get. And that really had an impact when people realized we could do that. And to this day, if you think about companies like Planet or Spire or even Skybox, which became Terabella and now is Planet, the way they build a spacecraft is not traditional. They do things differently. And I think that's kind of a little bit of the path that it took. The other thing that was in there that was very important, and maybe we didn't realize at the time as much as we should have, but the fact that we had a standard meant that launch opportunities were viewed in a very different way than before. There was a number of launch vehicles that started putting accommodations for CubeSats on those vehicles, and they did very interesting things. They would put accommodations on the rocket without knowing who was going to fly there, which is unheard of on the space business. But they knew that there's these standard satellites, and some will show up and will go fly. And in the same moment, that the satellite developers were like, well, we're going to start building the spacecraft, and then we'll figure out where we launch. And traditionally, especially like university satellites, we would always be thinking about what's the launch before we really committed to building the spacecraft, because you needed to have the right dimensions and make sure you fit, and which rocket is gonna let me go. And CubeSats kind of stopped that. And that was a kind of a confluence of very interesting, strange, non-traditional space things that came together that made it all happen. But it's a very interesting process that I think has some lessons for the future. And what we're seeing now, and I mean, at Tyvak, we're doing this where we take the philosophy that started with small CubeSats, and it keeps moving to bigger and bigger spacecraft. And now we're working on 50-kilogram satellites, but still primarily using commercial off-the-shelf components. We've learned ways to make those more reliable now, both by design and by redundancies and other things, but it's kind of different from the way it was done before. A lot of it was very well established and very immobile, and now we have a very dynamic, very vibrant industry where we're pushing things up. We start with small satellites, we test them in 1U CubeSats or 2U CubeSats. When things work, then they move up to 3Us and 12Us and 50-kilogram microsats, and the reliability keeps going up because people are learning and using lesson learned, and we're doing that very quickly because we get to fly very often. People will. Somebody was talking about the fly, learn, fly again philosophy, which was not feasible with $100, $200 million spacecraft because the initial cost is too high. But with CubeSats, you can do a lot of that. Did I answer your question? Because I know I just went on a rant. And
No.
That was great. You answered that question and about 3 more. So I'm fine with that. Chris?
I was about to ask how important the ISS is as a launch, not necessarily platform, but a secondary launch platform. But it sounds like it's been more the rocket providers making accommodations, even speculatively, that's really caused things to grow?
Well, that's how we started. We started with secondaries, and I think the station is it's all kind of this realization that people are getting comfortable with the concept. When we started, we had very few opportunities to launch. In the US, oh, that's too risky. Who's going to put these things on our rocket? We have a very expensive satellite on top, and as things flew, and I think that's one of those things. We were using the Peapod at the time, which CalPoly developed, the first deployer, and we were using the same thing every time. So by the time we had launched 10 or 12 of those and they had all worked and nothing had happened, people started saying, well, maybe they're not that dangerous. So we'll put them on our more expensive rockets. And I think the station was kind of the next step. Can these things go to the space station? There's astronauts. There's, safety was something that people were very concerned about. But everybody got comfortable with it because it flew so much and we were doing it so often and successfully that it's like, hey, yeah, we can do that. The other thing that happened that was very interesting is people started to realize that these things are really small. They don't carry large batteries. They don't carry large transmitters. They're pretty benign spacecraft and quite safe. But at the beginning, that was not the case. It was quite interesting.
Did you get a lot of pushback from the old space folks who considered a small satellite to be 500 kilograms? I mean, it just seems like someone would be saying, no, you can't do that. That's wrong.
It was really bad at the beginning. And I always tell people that one of the great things that helped us initially is that we had no funding. Because if we did, they would have canceled it. Because everybody would tell us it's too small. You cannot do anything with something that small. It's just a toy. It's a waste of time. And for us, it didn't matter because we were teaching the students, and that was we knew we could do that with those spacecraft. But there were some people that didn't even think you could do that. It's like it's too small. It's too different. It's not going anywhere. But no, we heard a lot of that in the beginning. It's quite depressing.
Yes, of course. Do you interact with the people who were naysayers then, who are now maybe converted?
Oh, yeah, we have lots of those. We have a lot of great supporters that I wish I had a recording because I remember what they said before. But it was understandable. I don't hold it against anybody that when we started, because we had to prove ourselves. And once we did that, the smart people changed their mind, which is the right thing to do.
You said that the students get most of the education from the satellite before it ever gets to space, which makes sense. The building is the educational part. Do you ever just not launch them? I mean, do the students graduate and you're like, oh yeah, it was going to be on the next launch. Goodbye.
Yes, that happens. And it's frustrating. And because the whole point is we wanted to get them to launch. And there's actually an interesting nuance to that sentence that it happens before the launch. And it does happen before the launch, but up to the day of the launch, because or the day you send it to the integration facility, because all the final testing and qualification is very important. And that's one of the things that was hard to do when you didn't have a launch opportunity. So these days, even when satellites, sit in a shelf for a while, they're usually completed and fully tested and ready to fly because they have a very good understanding of what their launch will look like, because they'll go in a standardized deployment mechanism, and that's the launch vehicle, and they can do it. Luckily, the life cycle of these things is relatively short. So what we find is with our students, for example, they'll probably, if they're around for 4 or 5 years, they'll probably be around for, or almost always will be around for a launch. It may not be the satellite they design, and that actually is another interesting thing where we'll have students do operations before they design, because there's this active lab that launches satellites, every year or two. And when you join the effort, hey, we're doing operations. That's what you're going to do. Go talk to our spacecraft. But yeah, sometimes satellites don't launch, but there's still a significant amount of learning that goes on through the process.
You said you didn't have a lot of budget to start this, and I understand for making the hardware, yeah, you don't need a huge bankroll for the 10 by 10 by 10 satellite, but launches still are quite expensive. How do you get funding for that?
Well, launches were not that expensive when we started. It was interesting. The first launch we did with CalPoly, we got a Russian launch for $40,000 a cube. So that was really, really cheap. And those prices have gone up. So you cannot do it at that price anymore. But in the US, we're fortunate because NASA, after a few years and a few launches of their own, with their own missions, they decided that this was really worthwhile. And they stood up the ALANA program to launch these satellites at no cost to universities. So as long as it's an educational program or it's flying missions of interest to NASA, they will try to find them a ride. And a lot of satellites in the US have flown without launch cost. In Europe, they have a similar programs with ESA. Japan has the same thing. India has similar things. So everybody's starting to see these as a very important workforce development activity and supporting the launch cost.
Do you know off the top of your head if Australia has that program too? Because I know there's one person who's just shouting at the show right now and wanting to know.
Yeah, I don't know. I know that Australia has very good connections with the United States, so we're trying to help as much as we can make that connection and see if there's a way to get some other university satellites launched. I know that they have a launch coming up from a mission that's a joint venture between Australian Ministry of Defense and a couple of universities. That's called Buccaneer. And I don't know exactly how the costing was handled, but it's launching on a U.S. vehicle. So
I think it's fascinating that they're supporting schools that way. It makes a lot of sense because it is not only a learning opportunity for the builders, but as you say, for the operation people. And you don't have to be at CalPoly in your operations department to listen to these satellites. Anybody can listen to them.
Absolutely. We actually, most universities will have ham radio beacons on their spacecraft. And that allows anybody with a ham radio setup to listen to the beacons. And actually during the early parts of missions, we find it very useful to have the ham community supporting the launch and listening for the satellites because we may have a few and it's hard to find them all.
It's on my list of things to try at some point.
It's a lot of fun.
I've watched some other people do some contacts, and it's you need 4 arms.
Yes.
To track the satellite and manage your there's some drift things that happen, but it sounds like fun.
No, and there's some automation that the software you can get out there is getting better. So that's a lot of fun.
How long did it take for you to think, well, let's standardize these satellites, make them small, and use them as learning ideas, learning tools? How long from this idea conception to the first launch of one of them?
That's an interesting question. And actually, that's an important point because it wasn't overnight. The first concept was 1999 is when we started talking about it because both Bob and I had experience with bigger spacecraft and how hard it is to fly them. And we were looking for a different way. Our first launch was in 2003. So that's 4 years, which is not terribly long.
That's fast.
That's fast, but then for space is very fast. But for CubeSats, it's actually pretty slow. The second launch was in 2006. So that gives you an idea that initially it wasn't this every 6 months you have a launch. That's 7 years. I think it took about, I claim, or I would like to say that it's about 10 years until things got really serious and people started realizing this is going somewhere. Which when you think about, standardization and coming up with a standard and putting it out, that's quite a while. And a lot of people are saying, no, we'll just come up with a new standard and then it'll be great. And it's like, yeah, it'll be great, but it may take a while. It's not going to be like a 2-year process.
Are there challenges you see every year with the students and their satellites? Or are there constant problems that everybody runs into trying to make a CubeSat?
Yes, yes. There is, and we get better, and there's tribal knowledge that evolves. But that's one of the big differences between industry and the university students. And I'm lucky because I get to see both. And we started the company and brought a few of our students back, and started working there. And I'm like, oh my gosh, that's what companies get when we send you guys out. Because in the university, one of the things that we have to be very conscious of is all the students is their first time. And for us as faculty, sometimes we want to go do the next thing. Because we did this already, let's yes. move to the next step, and we have to make those steps very slowly because the students are it's the first time, so that we'll make the same mistakes again because we're doing it the first time. That's what we're seeing, with some of the companies. They're doing it for the 15th time or the 100th time, and you really have it dialed. But the university is different, but that's the whole point. You're training people, and we do move forward and we do better things, but it's a different pace.
In general, what things do people keep getting wrong, both in industry and school? Because I suspect they're different.
Yeah, they're different, but they're similar in some ways. And actually, I would say that a lot of the things that people do keep having issues with in industry are very similar because it's primarily people that do this for the first time. And in some cases, even very experienced people may be doing a satellite for the first time. Like CubeSats have brought on a lot of payload developers that have decided, we'll do the entire spacecraft now. And that first time is more of a struggle than people realize because the integration process and the qualification process and all the testing and interfacing with the launch vehicle, that's still rocket science. If you've never done it before, it's interesting. The students have some issues, and this is just they're just learning. So I'm not trying to put them down, but there is a lack of understanding of the end when you start. So sometimes you're designing a spacecraft and you're not thinking about, I have to put it together and maybe I'll have to disassemble it because something will go wrong. We'll have a lot of people that will schedule testing the day before you deliver because you test and then you deliver. And he's like, no, you test to make sure that nothing goes wrong, which means most of the time something may go wrong. So let's put a month in there between testing and delivery. So there's a lot of things like that, putting connectors in places where you cannot get to because you've never put a spacecraft together. And that thought of, my hands need to fit in places may not come along. So there's some very interesting things that we keep seeing over and over. However, if you have if you pay attention, sometimes you can stop them before they become dramatic the second time around. Because then, some of the senior students, myself, we've seen it before, so we kind of prepare for it. And I think that's what ends up being the great thing with industry and with CubeSat industries that you gain experience very quickly because you build satellites frequently, and you get good at it, and you don't get rusty because you don't stop and now do design for 2 years and go build the next spacecraft. You have a team that's always building, always testing, and those guys get really, really good at it. So I'm hoping that answered the question.
So I'm interested to, because I don't really know. Can you describe the basic architecture of one of these? Maybe a student device. Like what goes into it electronically and software wise?
This is actually another thing that's very interesting because there's a tremendous diversity of designs and just philosophies. You can go buy yourself a spacecraft. And you get it, and then you put your payload, you integrate it, and you go fly it. At CalPoly, we started before there were commercial components. We developed a really good electrical engineering team that does a lot of our boards. But in any case, whatever you design it or you buy it or whatever, the architecture is very similar. It's basically a laptop. You'll have a microprocessor, ARM class in many cases, a few FPGAs that runs the show. Even more sophisticated satellites that need more computational capability may have a second computer on board, either for additive control or for the payload or for other components. You'll have some sort of power system that regulates solar power and charges and protects batteries. And then you have some sort of communications device. Lots of UHF ham radio systems, a few S-band systems are coming along, and now the more advanced CubeSats are moving into X-band and Ka and all the bands that are traditional in the space business. That's the core. And then you may have a pointing attitude determination control system with reaction wheels and star trackers or magnetometers or sun sensors, depending on what your requirements are. And at the end, you put a payload on the spacecraft to do something. And in some cases, the student satellites may not have a payload per se. The communications package is really all they fly, or they're testing some components in their spacecraft. We'll have universities that say, we're just testing our bus. We're making sure that the basic architecture of the spacecraft works, and then next time we'll put a payload on it. And then the payloads are all over the place. You have NASA payloads doing biology experiments. We have science instruments measuring the upper atmosphere, taking pictures of the Earth, going to the moon and looking for water. So the payload is a big open question. You can almost do anything.
I just have this idea of spores in space.
Yeah.
But I wanted to go back to, you have an ARM processor, but this is a big one. This is running Linux. It's really more like a laptop than what I think of as an embedded system, like a microwave or Fitbit. Okay.
Yes. And when we actually, like at CalPoly and Tyvak, both, we learn it's a Linux machine. You can log into the spacecraft and treat it like a computer.
This seems like a very interdisciplinary project. You mentioned software and hardware and placing connectors where you can get to them, which is definitely mechanical.
Yeah.
Do you end up with students from different majors, or is this an aerospace major that is learning lots of different things?
We have an extremely multidisciplinary team, both of faculty and students. We could not do this without software people and electronics students, as well as mechanical and aerospace. But it's truly a reflection of what the real world looks like. If you go to Lockheed Martin up there in Sunnyvale, they're not a bunch of arrows. They have everybody. We will have science students join us from physics to help with payload. So it is extremely multidisciplinary. And one thing that I want to point out, because of that, there's another interesting byproduct of the fact that we are very multidisciplinary and based on commercial electronics components. And that is that the training is not just aerospace training. We have a lot of the electronic students or the software students or the mechanical students that will go work for what you would consider, Silicon Valley traditional high-tech companies, the Googles and the Apples and the Facebooks of the world, because a lot of what they learn translates directly and on those devices. And it was a surprise to me initially how positively their experience on our satellites was viewed by companies like Apple. Well, they say, "Oh, wow, this is really good. You understand I2C, and you can, create all the power regulation for a microcontroller and use batteries and all the things that, to some extent, is the same thing as a phone. You just think about it, and there's radios in there, and you understand electromagnetic interference between electronics and the radio and GPS and all that kind of stuff. So we have found that these are extremely good systems engineering training packages for whatever you want to do when you get out.
And systems engineering is a great way to understand, even if you want to specialize in software, getting that perspective is amazing.
Absolutely.
When college students ask me how can they prepare for a career in doing embedded systems, I've always suggested joining the robotics team because it is so hands-on and so interdisciplinary. And you're talking me around to like, join the robotics team or your CubeSat team.
Yeah. And the reality that is very interesting is that in many cases, and we've had tons of cases like this, the training for some of those students is very centered around their discipline. So we'll have a lot of EEs that are very good at circuit design, but the idea that their circuit design needs to be made into a board that fits in a specific location and has bolts and connectors and screws and all that, that's kind of the next step. And same thing with software. You're building software, but now I need to instead of putting your software on a nice, well understood, stable, PC or Mac, you have to put it in a computer that's also part of the project. We've had a couple of times when we were developing a computer board and we were having problems, and the computer guys were finding them, but their initial reaction is the software's wrong, because that's the way it is in class. If you do something wrong, it's the software. It's never the computer. and it was like, wait a minute, it could be the computer. And they're like, oh my gosh, you're right. It could be the computer because it's new, and it was the computer. So that's a great experience for them.
Given that it is their first time working in this sort of environment, and that they don't have preconceived notions about what satellites should be or what they should do or how it should all go, have you ever been surprised by something that a student did because they didn't know it was impossible?
Yes, and actually that's when we talked about the fact that CubeSats were successful because people use components and methods that are not used in space. That was the great advantage they had. They didn't know that you're not supposed to do it that way. And we actually had some students that said, we're going to put a camera on a CubeSat, and we're like, no, it's not going to work. Because the cell phone camera will never work in space. and the next thing we know, they're sending us pictures. Look, we did it. So not knowing what you're doing, it's a big advantage when you're dealing with highly innovative environments. And we have to be very careful because we were all in this innovative mode, 15 years ago, and now we think we know how to do it, which probably means some kid will come up and try to do something that we think is really crazy, and it will work. So that is a good thing, and I think we should provide them guidance. And there's some things that don't change. Vibrations are like this, and they're gonna shake your boards really hard, so you need to make sure they don't fall apart. But there's a lot of opportunities for doing things differently that do work if you do it right. And one thing that's nice with CubeSats is we're trying everything. I mean, we're flying so many of them that we're trying lots of things, and some don't work, and some work. And every once in a while, there's a brilliant one. There's like, oh my gosh, that works and works really, really well, and that moves on to bigger satellites.
So switching subjects a bit, you are one of the organizers for the CubeSat conference in April. April 26th to the 28th in San Luis Obispo.
Correct.
Who should go to that?
Everybody should go to that. It's actually interesting because there's lots of conferences and lots of workshops, and we work very closely with the Small Sat conference in Utah in August in the summer, which is a huge event. But one of the things that we've tried to do since we started this workshop, and the reason we started it's to be extremely CubeSat focused. So it's the very small satellite conference, and we want to keep it that way. And one of the things that does is it brings together people that have very, very similar problems, and that's important because you get to talk with everybody that's working on these really small satellites. We also try to cater to new developers. There's a lot of people starting on CubeSats. And when we started, it was easy. Everybody was in the same boat. We were all kind of trying to do these very simple missions and get them to work. Now it's more dangerous in a way because you start and you see what JPL is doing or what Tyvak's doing or what other companies are doing, and they have these phenomenal CubeSats that can do all kinds of stuff. And the temptation is to just go there on your first mission, and that's that's not going to work. So we do spend a lot of time kind of talking with new people. A lot of new developers will come up and talk with teams that have more experience, but a big theme is to try to help out and give people advice on how to get started. And remember, and we try to allocate a few presentations every year for new teams, even if they're doing very simple things. We'll have high schoolers come and talk, because we want everybody to remember that there's a bunch of people out there that are doing it for the first time. Just be nice to them and help them out, and give them credit for what they're doing, even though it's not the most advanced CubeSat ever.
When you were in high school, could you have imagined that high school students now could send things to space?
When I was doing my PhD, I couldn't imagine PhDs would do a satellite. No, no, absolutely not. I mean, the idea of student satellites at universities, when I was at university, it was like, yeah, MIT may do it, Stanford's doing it. It's a few schools. It's extremely difficult, and now high schools are doing it, and they're doing it successfully. That's the. I mean, it's not just like, yeah, they're trying, but they're not going to go anywhere. I mean, we're working with a couple of schools. We're working with Irvine School District and a school in Florida. And they're being very successful. Part of it is there's a whole infrastructure now that you can go and get help and get parts and get support that was not there before. And I think it's like everything in technology, like you have a computer in your desk that's more powerful than the Apollo systems, and everybody uses one. So technology kind of trickles down, and at some point, high school started doing robotics, which was like, oh my God, robotics was this really advanced thing. And now that's an easy segue into, it's the same idea, you just put it in space. And I think it's marvelous that they're doing it. Kind of, I still pinch myself sometimes because it's crazy. But yep, it's happening.
It's crazy and amazing. And what will they be amazed by when they're our age and some high school student is doing something they couldn't have imagined?
Preschool students will be sending satellites up.
Yeah. No, I mean, it's really impressive what happens. And the thing that's very interesting that I'm very proud is there's a huge motivator. Everybody talks about how, fourth graders are into dinosaurs and space, and I cannot bring dinosaurs back. But I can maybe make them feel like they can get to space. So that's been great to see, because we have, whenever we've worked with high school students, the percentage of those students that pursue careers in science and engineering, whether it's space or biotech or cell phones or whatever, it's extremely high. And I think a large part of it is, one, they realize that this is really exciting stuff, and it's actually kind of cool to do science and engineering. But the other thing that I think happens is that if they can do a satellite, they feel like it can do anything. And at that point, the sky is no longer the limit, and they just feel extremely empowered.
Okay, changing subjects again. Tyvak. It's a company you co-founded to bring some of these lessons learned about CubeSats into industry. Is that right, or was it founded for a different reason?
Of things, but there was a few things that were happening. CalPoly was doing a lot of launch activity as kind of a sole source, because we were the only game in town, and at some point it became more of a commercial activity with a number of companies participating, and we decided, well, it's not really something. The research part is done. The university should move away from that. And let the industry do it. But a few of us and a few of the staff said, well, but we're really good at this and we want to keep doing it. So let's start a company that can do that. So that's one of the sides of Tyvak, which is the launch and integration services component. And then the other part was this idea that we kind of knew what the next thing we would do would be if we could continue, it's like, we've done this satellite and we've learned all these things, and now the students graduate and go work for somebody else. But if we could keep them, what would we do? And and we decided, oh, there's all these really interesting projects that we would like to do, and we think we can get the funding to do it. And that's kind of where the nugget of the whole idea came. We decided to do a company that's in some ways different from some of the companies that were evolving at the time. There was a number of companies, Pumpkin and Gumspace, were selling components. We saw that as it's an interesting market. And then Spire and Planet were mission companies that were like, we're going to image the Earth, we're going to go track ships, we'll do something. But we felt there wasn't anybody that was saying, okay, we're going to be, the Lockheed of the small sats. When JPL wants to fly a mission, they need somebody. When somebody has a payload they want to fly at the very high end, they need somebody. And that we felt that was an open niche in the industrial fiber or ecosystem of CubeSats, and that's kind of where we went, and it worked fairly well. We're still alive, which as a startup, that's always a great thing to make it past 5 years and beyond. And one of the things that has happened is we have learned what the capabilities of these satellites, when you go and push the envelope technologically with a very experienced team, then you can start looking at payloads that are beyond what you could do with CubeSat. So we're looking at 12 U's, and we're looking at 50-kilogram satellites that can do synthetic aperture radar or high-definition imaging, signals intelligence, all kinds of things that you never thought you could do with small satellites. And the same way that you can do amazing things with a 1U, if you apply the same philosophy and the same principles to a 30-kilogram spacecraft, you can do really impressive stuff.
I imagine. What about the other way? Have you ever looked at doing even tinier satellites?
We actually, there's a few groups looking at, we have pocket cubes, which are, like 5 centimeters instead of 10 centimeters. We've seen fractions of a U's, like half a U, where it's 10 by 10 by 5. And we have seen a few efforts to go that way. And I think that that's going to be the tech demo satellites for CubeSats will be those satellites where we'll test new, smaller sensors and components. What we have seen is that the 3U, 1U is really small. And we're trying to push the envelope what you can do with those and keep moving the capability out while maintaining the size, instead of looking at smaller satellites with lower capability. And there's an issue from the commercial side. You have that there's a utility line where you need to get the thing funded, and it needs to do a certain amount of stuff. And then that the amount of stuff you can do on a 3U keeps going up, but you have to do a minimum. But we've done some 1U missions, and they've been successful. So there's a lot you can do with a small satellite, but we haven't pushed really hard onto smaller than 1Us.
That makes sense. I just am boggled by the idea that you can do something in this 1U 10 centimeters cube. And as I say that, Chris is holding up his iPhone and pointing out that you can do a lot more.
What's interesting is, and this is one of the, there is a curse that comes with standards. And that is that once you standardize something, it's very easy to do things if you match the standard. If you go away from it, it's harder. So coming up with a smaller standard or doing things smaller, it's hard because it's so easy to launch 1Us. So that's an interesting potential negative with standardization, is that now you're stuck with this 10 centimeter by 10 centimeter. And why is it not 12? I don't know, because it was 10. And, that the lighter connector on your car, that's everything that you buy to connect electrically to your car uses this connector that makes no sense as a connector. And it was really funny. We were talking, I was talking with my son recently, and he thought that people call it the lighter plug because that was the name. he had no idea that actually was a lighter when it was first designed, because he's never seen one. And I realized, he's never seen the actual original use for this thing that created all the specifics of the standard. There's a plug in the middle and the things on the side, and all that was to light your cigarette, and now it's how you pump your tires in the middle of nowhere.
Yeah, we used to put a facility for you to light small fires inside your car. It's perfectly fine.
Do you have any advice for someone who's listening out there who wants to get into aerospace, but isn't it CalPoly and in your department?
Well, they would be much better off if they were CalPoly in my department. I'm just joking. I think it's a tremendously valid and tremendously rewarding career. I think if you have a passion for space or for aerospace, you should go for it, and pursue it. Even though sometimes, I've heard a lot of parents concerned that their students are going into aerospace engineering, but that's limiting their options. I'm like, no, they're going to be great engineers and they can do all kinds of things. But that actually works the other way. If you're very interested in physics, don't become an aerospace engineer, become a physicist and go into space to do physics. If you're really interested in electronics, but you want to work in space, pursue a career in electronics and then do electronics in space. Software, we need everybody. So pursue what you're passionate about, and everything can take you to space. And actually, we've had students working with us from liberal arts, from graphic arts, from journalism, and they're tremendously valuable members of our team. So that's what that's one of the things that I think is important to tell people sometimes, is that you don't have to be an aerospace engineering student to work in aerospace, but you do have to be passionate about it, and then just go do things that you're good at and you enjoy, and work in that direction.
That sounds like good advice for all kinds of careers.
Yeah, and I think it's truly advice for all kinds of. And these days, a few years back, if you wanted to work on cars, you have to be a mechanical engineer. These days, I don't know. I think we probably see more software engineers working in cars than mechanicals. So,
for better or for worse.
For better or for worse, yeah.
So I wanted to ask you to look to the future a little bit, and if launch costs come down, like SpaceX is trying to do, if they make reusability a thing, how does that change things for CubeSats if, say, launch costs are cut in half or down to a quarter? Does that mean more risk, more innovation, or does it just mean more satellites?
That's an interesting question. And I think one of the big risk reducers, or one of the things that reduce the risk posture on satellites is launch cost. And when you start thinking about, a big rocket costs hundreds of millions of dollars, lowering the cost of the spacecraft by increasing risk doesn't make any sense, because your cost will not go below the cost of the launch. If that number goes down, the ability to take risk really goes up. And with CubeSats, we are already low enough that people feel comfortable taking some risk. But it's a big investment, when you have a $250,000, $300,000 launch cost for a 3U, that is a steep check to write. If you lower that number, then you get to innovate even more. And I think it's not just more satellites, but I think we'll see more people having access, which means more ideas being tried. And that's only a good thing.
Is there a limit to how many of these we can put up? I mean, they all have to be tracked, right? And there's always this question of debris.
The big debris question, I always brace for it, because
sorry,
it's like it's your fault. You're putting all this garbage up there, especially when we were doing a lot of university satellites. Where with many universities, the first satellite, hey, if it works for a few days, we're awesome. We did great, but then it stays in space for a while. We're very conscious of the rules, and most of the CubeSats these days are launching into relatively low orbits. Well below the limit, which is 25 years. station orbits last 6 months, 3 months. So they're out of there very quickly. An example, or to see the numbers, we put about 500 and something CubeSats in orbit total. More than 100 were from stations, so they're not there anymore. So and then of the others, many were low that are back on deorbited and burning the atmosphere. What we're seeing is we're probably going to reach a steady state that's not as large as people think. Maybe we'll get to the thousands at some point, but maybe not. And as an example, the Chinese intercept test was many thousands of objects being deployed into space or created as debris in a single event. So I don't think we're going to be responsible for a large percentage of the object being tracked. I think right now they're tracking like 20,000 or 23,000 or something. However, people are talking about very large constellations. SpaceX is talking about thousands of satellites, and OneWeb is talking about many hundreds to 1,000. And those constellations will be interesting to see how we handle the collision risk and all those kinds of things. And those are not CubeSats; they're bigger. Yeah. But yeah, debris is an important issue. I just do not think CubeSats are the big problem that people like to say sometimes. They're there. They're players like everybody else. But we're trying to do our best to play by the rules and minimize our impact. And I think we're doing a good job at that.
Cool.
And I think the planned obsolescence that is built into CubeSats allows for a bit more risk as well. They're not supposed to be there for 50 years.
Right.
No. And actually, that's one of the things that was very interesting when we were kind of challenging the traditional space people, and we're saying, you guys are using technology that's 10 years old. So we're going to use the latest and greatest. And one of the things that we didn't realize is that we also had a tendency to become attached to things we had tried before.
Oh, yeah.
And it's like, oh, but I've flown it before, so I'm going to use it again. And one of the great things about using commercial off-the-shelf components is that they stop making them when they're not at the top of the hip. So you have to plan for, we will have to change them as the industry evolves, and these other markets are investing billions of dollars in making better components, and we'll have to just follow what they do. The one thing that has happened though is a lot of the effort is being in learning how to use those things in space and minimize the risk. Built-in electrical and software redundancies that help you with some of the things will go wrong because the parts are not space qualified, and radiation will have an effect, and we'll have flat chaps and single event upsets, and we have to find all these tricks to minimize how that hurts us. And those tricks work whatever the parts are. So as the new model comes out, you get a lot of confidence that, well, I've flown this architecture before. The camera is new, but it's just an upgrade of the one I already flew. So people are getting kind of comfortable with that mentality that the fact that it's a new specific component carries the same risks that we always fly. The fact that we have an architecture we've proven before that we feel is, or we know is robust and reliable, that remains.
That makes a lot of sense. Well, I think we have kept you for about long enough.
Wow, right. I just realized how late it is.
Then, Jordi, do you have any thoughts you want to close this with?
Yeah, and I don't know if we've made these clear, but one of the things that I always like to get out there is that one of the reasons, or one of the most important things that made CubeSat successful was this move to use things from a different industry. We were using things that were developed for cell phones and laptops and things like that. And I think in the current technological climate, when there is so much going on, so many changes, so many advances in materials, in all kinds of things, in electronics and software, that's a very important thing to do. To be capable or spend the time or have the disposition to look outside your area of expertise and the group of people that you work with and the traditional methods that we've always used, and go see if there's something out there that somebody's doing for a completely different application, that all of a sudden you go, oh, wait a minute, what if I use this for something completely different? And we've seen that be extremely successful in space. And I think we have lots of examples of those kinds of things happening in other industries. But I think it's amazing how difficult it is to do it, because we all tend to like our own stuff and be very good at something and be experts, and then we stay within that world. So just something for everybody to think about. Whatever you do, whatever your industry is, every once in a while, take a glance sideways to what those guys over there that are doing something different are doing. And every once in a while, there may be a surprise.
Cool.
That is excellent. It has been wonderful to talk to you, Jordi.
Thank you. It was a pleasure. And if you guys have the time, just come for the workshop. It's a lot of fun.
It's just really tempting.
We hope the weather will be good. So.
Maybe. I mean, April in California is often very nice.
It is indeed. So, and you guys are not that far away. So,
before we go, you're hiring at Tyvak, and we should note that because you are hiring for hardware and embedded software and software people, and it's in Irvine. Is that correct?
Correct. Our main operation is in Irvine. We also have a small office in San Luis Obispo that does the launch services, and we have a small group working out in Colorado, and we're starting to have some people in DC as well, because as we get more contracts with the government. So we have people in several places, but the primary job location is Irvine, which is not a bad place to be, and we do hire everything, software, hardware, electronics. And one of the things that's interesting was we've been very successful at creating a group of people that has a very good mix of traditional space people, as well as people that come from completely different markets and bring that expertise to the table. And that combination has been very successful. So we have a number of individuals we've hired that were not coming from the aerospace industry, and they're great contributors. So I would say if you're interested in space, even if you're not a space person, there's still a spot there for you.
All right. Thank you.
Thank you.
Our guest has been Jordi Puig-Suari, professor of aerospace engineering at CalPoly San Luis Obispo and co-founder of Tyvak Nano-Satellite Systems. If you want more information about the available careers, it's tyvak.com/careers. That link will be in the show notes, along with the link to the CubeSat conference, although CubeSat.org is pretty easy to remember, so you can do that. I would like to send a special thank you out to Stuart McAndrew for sending me some excellent questions. Stuart has been working on his own CubeSat for a while now. It's an Arduino-based educational satellite. I have to say, there's nothing like sending something you've touched to space. More info on his satellite will be in the show notes. Thank you also to Christopher for producing and co-hosting. Jordi doesn't know this, but his microphone came from our supporters at Patreon. Thank you for making it easy for me to drop ship mics to interesting people. It makes my life much easier to just make that decision. And whether you are a Patreon supporter or not, thank you for listening. A final thought to leave you with, this time from one of my least favorite great literary figures, Henry David Thoreau. You must live in the present. Launch yourself on every wave. Find your eternity in every moment. Fools stand on their island of opportunities and look towards another land. There is no other land. There is no other life but this. He may be kind of a dweeb, but he can write pretty well. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.